Good morning, friends. My name is Ashutosh Garg. I work as a solution provider with Furnace Improvements. Our company is in the business of revamping fire heaters. We convert your fire heaters to highest capacity, longest run length, and lowest emissions. This webinar today is born out of our experience in dealing with end customers for more than 40 years. This is our second webinar, and I welcome you all. Currently, the whole world is experiencing COVID pandemic, and I hope all of you are keeping safe and following all precautions. For the next hour, we will be talking about fire heaters. Fire heaters, as you all know, are one of the largest equipment in the refineries and chemical plants. They are very unique equipment. It is very easy to overfire a fire heater like a balloon. Any mal-operation in fire heater can be very expensive. They are also major consumer of energy in refining and petrochemical industry. So we are going to focus today on a new technology for increasing the capacity of fired heaters. And it is my hope that by the end of the webinar, when you go back to your units, you would be in a better position to evaluate the performance of your fired heaters. Learning is a continuous process. We have learned so much in the past 1 month while preparing for this webinar. So please don't hesitate to ask a question. Please feel free to share your experience with us. You are in the field working with fire heaters day in, day out, and know much more about furnaces. We are going to conduct this webinar today through PowerPoint presentation. We have been able to improve our webinars based on your feedback from our past participants. We request you to kindly complete the survey before you leave and send it to us. I will start the session with a brief introduction of myself. I'm a chemical engineer. I passed out in 1974 from IIT Kanpur in India. I worked in an ammonia plant for 2 years. And since 1976, I've been working on fired heaters and combustion systems. I have worked in KT India, Engineers India, and then KTI Corporation US. Since March 1996, I've been working at Furnace Improvements, fixing heaters for the past 24 years. So our presentation today will be for 50 minutes, and then we will have a 10-minute question and answer session. So please keep on sending your questions to us, and we will answer all of them at the end. So I want to start out by thanking our team in the US and in New Delhi, they have been working very hard for the past 4 weeks. Our team of process, mechanical engineers, admin team has been working and putting this presentation together. It is all their hard work which is you are seeing. I am just the presenter today. We want to make sure that everybody is able to log into the webinar correctly. I am showing you the slide for when you log in, you see this control panel and you can select the voice source. There is a question box available and you can keep on sending these questions at any time. You can minimize the control panel on your screen by hitting the top red arrow. We will make the webinar recording available to you in case you are not able to sit through the entire session or you miss any part of the presentation. If you are not able to hear us clearly or has a display issue, please send us a message and my colleague will be able to take care of the problem. So I want to give you a brief introduction of our company. Furnace Improvements was started in 1996. We will be completing 25 years in business next March. We have 3 offices. The head office is in Sugar Land, Texas. We have an engineering office in Noida, India. It was started in 2005. We have about 35 people in that office. They are doing everything, process, mechanical, designs, as well as drafting. We are a full service heater company and we can execute projects on a turnkey basis, including erection. Our CFD office was started in 2014. It is located in Pune. Our CFD team has been working exclusively on combustion, heat transfer, and fluid flow problems. We have been working on improving the performance of existing fired heaters. More than 90% of our business is revamping fired heaters and fixing old fired heaters. We try to breathe new life in these furnaces. So our focus or our business model is working directly with the end users and trying to find out what are the issues they are experiencing in their fired heaters. And we try to provide them unique value-added solutions. We have a little bit of contrarian approach and we have challenged the conventional way of designing fired heaters. And today we will be presenting one of the approach, what we call a split flow. So we will be showing you split flow, which is basically parallel processing. And we'll be talking about it today. So one of our clients had a 4-cell platformer heater. I'm sure all of you know platformer heater or a catalytic reformer heater. The flue gas temperature leaving the stack was 1100 degrees F. Client did not want any air preheater or steam generation for improving the efficiency of the heater. They called the OEM and requested them to develop a proposal for efficiency improvement. The only option available was to preheat the feed in the convection sections. The heater vendor submitted a proposal for adding new convection sections for recovering heat for $6 million. The client called furnace improvements. They told us to look at the heater and develop an alternate efficiency improvement scheme if possible. They were looking to reduce the cost of the project. We reviewed the heater design and its operating data. We told the client that we can do this job for half the price. It took us 3 months to convince the client we could really execute the project at half the cost. And finally, they awarded the project to furnace improvements and we executed it successfully. We were able to reduce the flue gas temperature from 1100 degrees to 480 degrees. We improved the heater efficiency by almost 20%. This one heater alone made a big difference in their entire refinery EIS, the Solomon Index. The capacity of the platformer heater was increased from 18,000 to 26,000 barrels per day. The efficiency improvement project paid out in 6 months. And this was the beginning of the split flow. Since then, we have implemented about this technology in about 12 heaters. And you can see on this slide a heater before the revamp and other side the heater after the revamp. And the piping which you see on the right hand side is basically the split flow piping. So we are going to be talking today in this webinar. First, we will discuss the conventional approach to revamping heaters for increasing capacity or efficiency. Then we will discuss the new approach, that is the split flow technology. We will review the advantages of split flow over the conventional revamp. We are presenting a case study today where we saved our client $6 million. We revamped the heater for less than $1 million. In the end, we will have a question and answer session. I take this opportunity to thank all our clients for giving us an opportunity to revamp the heaters. And provide them with unique solutions. In several cases, the client installed our technology for the first time, so they were taking a big risk, but in most cases, it paid off. So I'm presuming all of you are familiar with fired heaters. I'm showing two sketches. The first sketch is a typical fired heater. The feed enters the heater in convection section, and then it goes to the radiant section, and then once it is preheated to the required temperature, it goes out. So the feed is heated in series, convection and radiant, and the number of passes in the convection and radiant section are the same most of the time. And this is the heater, the case study heater, which we'll be talking about. And you can see on the right-hand sketch, we have this feed in going at 611 degrees and going out at 720. It's a two-pass all radiant heater. Now we want to tell you that in radiant section, burners are fired, and the flue gas which is generated before giving heat is almost like about 3200 degrees F. Flue gas temperature leaving the radiant section is close to 1500 and 1600 degrees. Two-thirds of the duty is absorbed in the radiant section, and one-third is typically absorbed in the convection section. In the convection section, we are showing you boiler feed water coil, steam superheater coil. So it is a waste heat recovery system, and we are cooling the flue gases to 400 degrees before they are sent out to the stack. So this is basically what a typical heater looks like. So before we start discussing, I thought of talking about some very, very basic heat transfer and fluid flow parameters, correlations. And we will start with discussing the first coefficient, which is the inside heat transfer coefficient. Normally we call it HI. And inside heat transfer coefficient is nothing but ability of the fluid to remove the heat quickly from the inside of the metal wall. And if you look at this correlation, the heat transfer coefficient is directly proportional to the mass velocity raised to the power 0.8. I don't want to make it too technical, but I just want to give you a little bit of basics. Especially we'll be talking about what happens when we revamp the fired heaters. So as you can see, higher mass velocity will lead to higher heat transfer coefficient. Heat transfer coefficient is also inversely proportional to the diameter of the pipe or tube in which the fluid is flowing. That means for everything being the same, the heat transfer coefficient will be higher in 4-inch tube and it will be lower in 6-inch tube for the same things. So smaller tubes are always better for heat transfer. In fired heaters, we are mostly heating hydrocarbon fluids, and these hydrocarbon fluids are prone to cracking and coking. So there is another parameter we want to talk about, and that is the film temperature. And film temperature is basically the film temperature rise is defined as the average heat flux divided by the inside heat transfer coefficient. And if you want to calculate the maximum film temperature, we are talking about maximum heat flux divided by the inside heat transfer coefficient. And as the film temperature increases, there are more chances of coking of the fluid, and you don't want any coking taking place in your fired heaters. So with that said, you want to keep the film temperature as low as possible in your fired heaters. The third parameter we want to talk about today is the pressure drop. And pressure drop across the heater is proportional to the square of the mass velocity. So if the mass velocity is doubled, the pressure drop will be 4 times. It is also proportional to the length of the pass. So basically, the higher the fluid has to travel, the more will be the pressure drop. Pressure drop is also inversely proportional to the diameter. And what it means is, if everything being equal, 4-inch tube will have a higher pressure drop as compared to the 6-inch tube. So these are very, very basic correlations. And the reason I'm explaining these to you is, when we work with our clients, we have an open book approach, and we want to let you know what you are getting. Your job is to run the refinery and make money. Our job is to make these heaters as best as possible in terms of operation, whether it is a run length, efficiency, capacity. That's what we do for a living. So that's what we want to. We can explain all these things in an open book approach, give you everything. So let's look at the heater revamping. Most of the time, refineries keep on changing their feedstocks and operating conditions to maximize the product. Our experience shows that fired heaters in most refineries are never large enough, and they are always limiting most of the time. Client wants to get more capacity from their fired heaters. The capacity increase in heater typically consists of two major requirements. Most of the time, it is an increase in the charge rate, and that increase in the charge rate could be anywhere between 10 to 25%. Many times, the heater inlet temperature is lower due to the falling of upstream heat exchangers. And this basically leads to higher heat duty because the outlet temperature is fixed. In some cases, the client wants higher vaporization, so that leads to increase in the duty, or wants a higher outlet temperature because they want to have more reaction. So that's basically how the increase or revamping of heaters is carried. So anytime you want to increase the higher duty or higher charge rate, it will lead to higher pressure drop, higher firing rate, higher flux, higher film temperature, and most of the time you will end up adding area either in the radiant section or in the convection section. So the conventional approach for heater revamping is, there are two approaches. Option one, increase the number of fluid passes. You are increasing the fluid rate by 25%. You have a 2-pass heater. Hey, let's convert it into 4-pass heater. When we do that, the tube size is kept the same, and both convection and radiant section needs to be retubed completely. Now, you may ask a question, why not go from 2-pass to 3-pass or from 4-pass to a 5-pass? Why do we go from 2 to 4 or from 4 to 8? And the answer is, most of the heaters, it is not possible to divide the coils symmetrically in 3 passes or in 5 passes. So that's what happens is, heater vendors end up going in steps from 2 to 4, 4 to 8 to keep symmetry. It is hard to divide a convection section with having 4 tubes per row into a 3-pass. So that is one option. The second option is, the client says, I want to keep my heater to be 2-pass, and we end up increasing the tube size. If we have a 4-inch tube, we go to 5-inch tube. If we have a 5-inch tube, we go to 6-inch tube. And this change is even more extensive, actually. Here, not only we have to retube the radiant coil, we need new tube supports. We need completely new convection section. We can't even use the existing convection section. So as you can see, both these approaches are very, very expensive, So you can see the typical schematics. What we have shown you is a 2-pass going to a 4-pass heater, or a 2-pass heater remaining as 2 passes, but increasing the tube size. So, and what I want to tell you is, I think if you're only looking for 10, 15, 20, 25% increase in the capacity or in the duty, both these options have downsides. And maybe the heater vendor never told you, the licensor never told you what are the downside of these modifications. So let us look at. So we are giving you a two examples comparison. We are comparing a heater where the feed flow rate was 150,000 pounds per hour. It was a 2-pass 4-inch NPS coil. The mass velocity we calculate is 260, and the pressure drop is 100. Now let us say you want to increase the charge rate by 20%. So the feed flow rate goes up by 20% and goes up to 180,000 pounds an hour. Look at the mass velocity. The mass velocity drops from 260 to 157. So it almost drops by almost 40%. And look at the pressure drop. If the pressure drop across the heater was 100 pounds, now it has dropped down to 18 pounds, almost like an 80% reduction, because the pass length is half. Instead of 2 passes, now we have 4 passes. So the fluid is only traveling half the length. Mass velocity goes down. And all these things, if you can see, lower mass velocity will have lower heat transfer coefficient. Lower heat transfer coefficient will give you rise to higher film temperature, will lead to more coking. And we have a case where the client changed their crude heater from 2-pass to 4-pass and experienced almost 10 times the relative coking rate. So in my thinking, this is not a good approach. The conventional approach is not a good approach. It does affect the run length and coking rates. Let us look at what happens when we go for increasing the coil area pass, actually increasing the coil size. So same example, we are converting from 4-inch to 5-inch. The mass velocity again goes down from 260 to 200, almost like 25% reduction. Pressure drop goes down from 100 to 37, which is about 60% reduction. So in this case, we will be putting tubes at 10-inch spacing. So the length of the passes will be 4/5 as before, 80% reduction. I mean 80% of the original length, and mass velocity is decreased by 24%. So again, when you reduce mass velocity, when you reduce pressure drop, you are paying the price in terms of higher film temperature, higher coking rate, and shorter run length. And that is what we try to optimize. We try to say, if we can go for 100, or if the client can give us 100, why go to 18 or 37 and kill the pressure drop in the control valves rather than using it for useful purpose? So anytime you are talking about increasing capacity, we have to increase the heat transfer surface. In fire heaters, there are two sections. There is a radiant section where 70% of the heat transfer takes place. And then there is a convection section where 30% of the heat transfer takes place. And most of the time, you will find that increasing the heat transfer in the radiant section is not possible. And if you want to put more radiance, more surface in radiant section, you either have to extend the radiant section as we can see over here, or you have to put a radiant section separately. And both these options are prohibitively expensive actually. We convinced a client, this is a platformer heater. We convinced a client, this was recommended by licensor. We convinced a client to go for the split flow, and they saved almost 70% of the cost by going with the split flow technology and increasing the heat transfer area in the convection section. So anytime you want to increase the capacity in the radiant section, if you have a vertical cylindrical heater, you cannot increase the diameter, you have to increase the height. If you have a cabin heater, you either increase the height or you increase the length. And anytime you do this, you are talking of big, big dollars. So even though convection section absorbs 30% of the heat duty, it has a lot of potential to expand. So convection section is typically sandwiched between the radiant section and stack. And replacing the convection section with a larger convection section is much easier and uh, much easier exercise as compared to radiant section. Uh, we can keep on adding heat transfer till we get an approach of 25 degrees with the flue gas temperature. That's how much we can go. There is practically no limit. And we have focused on convection sections in all our split flow technology. Uh, this is an example of a convection section revamp project we did for a client last year. This is for a crude heater. And you can see the existing convection section and the proposed convection section. We doubled the width of the convection section. We literally doubled the height of the convection section. And we ended up putting more than 4 times the surface. And you can see we increased the convection section duty from 35 to 98. And we reduced the temperature of the stack from 600 to 300. This is a natural draft furnace. So by doing this, we were able to solve many problems of the client. Client had plenty of heater. The original heater was draft limited, air limited. Once we reduced the pressure drop in the convection section, they could put as much fire, they could put as much air, all the problems were taken care. So let's talk about the split flow technology. And the concept is very, very simple. All we are doing is we are dividing the process fluid into 2 parallel streams. The main stream continues to be heated as before. We don't touch it, mostly in the radiant and convection section. And we take the extra flow rate, split flow rate, and we heated it up in the convection section. And then the 2 streams combine at the heater outlet. We are basically balancing heat transfer and pressure drop. And you can see in the sketch, we have the orange pass as a split flow pass, which is heated in the convection, and then it is meeting with the outlet. So by doing this, we have several advantages. The first is we are not touching the radiant section, so the cost is very, very low. We are not doing anything to the radiant section in most of the projects. So the cost is very, very low. And we are only working on the convection. And here we can optimize the pressure drop. We can select the pipe size, number of passes in the split flow, and make sure that we get the best heat transfer coefficient, best pressure drop, best run length, everything we can control. So that's basically what we want to control. The other thing what I can do is I can keep on adding more surface in the convection and shift heat duty from the radiant section to the convection section. So that also unloads the radiant section, and that also works out very good. So this is a example of another heater, a 4-pass heater converting into 5-pass heater. And all we are doing is we are taking extra charge, finding space in the convection section to pick up the heat, and we are converting the 2-pass heater to 3-pass heater or 4-pass heater to 5-pass heater. Modification in the convection section only, and as I said, this works out very, very inexpensive, and it serves the client's needs actually. We really don't have to work on the radiant section or retube the whole heater for increasing the capacity just by 10% or 25%. A lot of people have talked to me about the how do you control your split pass. And I want to show you on the left side, we have a conventional heater, a 2-pass heater, where each pass flow is controlled by a control valve, and then the outlet temperature is controlled by a TIC, PIC, or TIC, FIC standard fuel gas loop. And in the split flow, all we are doing is we are treating the split flow as a second pass, as an additional pass, and we are having a temperature controller at the outlet of the split flow. And that temperature controller is getting the signal from the main controller so that both the temperatures are the same, and the flow is adjusted so that the outlet conditions both for the main flow and the split flow is the same. So it's basically like having another pass control uh, service. So these are the features of split flow technology: higher capacity, higher efficiency, optimized pressure drop, lower firing rate, lower firebox temperature, lower radiant heat flux, lower tube metal temperature, all these benefits. We have even improved our technology, and now we can even do split flow coils which are designed for dry run. I mean, we had one client who wanted to maximize the steam production. So he said, I want to run the split flow coils dry. And I said, okay, we will design it in such a way so that we can do it. So I want to talk about a heater which we revamped for one of our clients. This was for a job in Texas. We saved the client $6 million. And we have been working with this client for almost 20 years now. And our approach has always been to diagnose the problem and address the root cause. And we don't feel like selling you unnecessarily hardware. So this was a heater, a cabin heater, a 30 million BTUs, cabin heater with a central bridge wall, natural draft. Convection section was added later with a steam generation, steam superheater, boiler feed water coils, and it had a single stack with external support. So since they were added, the foundation was limiting and it was external supports. So the radiant section, very standard cabin heater, 6-inch tubes, 26 tubes at 18-inch center, and 2 tubes on the roof at 12-inch center, 50-foot long, 347 material, and average heat flux was 11,800 or 12,000 BTUs. The convection section had waste heat recovery added, and they were cooling the flue gas all the way from 1600 to 400 degrees. 16-foot tube length and 11 rows in the convection section. Burners, we had 2 rows of burners. There was a central bridge wall, and each burner was 2.3 million BTUs per hour. You can see the burner heater operating before we revamped it. So these are the parameters, and we checked the design: 30 million BTUs, 18 million for the waste heat recovery. The fuel firing rate was 55, and the heater pressure drop was about 62 psi. So that's basically the heater operation was. And client undertook this GST expansion project, and they said, hey, we want to increase the process duty to 37, so an increase of 23%. Firing rate, they had a limit on the firing rate permit. They didn't want to exceed 55 million BTU, so that was a major requirement. And they also wanted to reduce the pressure drop from 62 to 25. So they had a charge pump limitation, and they were adding a reactor in the circuit. So they took the pressure drop from the heater and gave it to the reactor. So they didn't want to change the charge pump. So basically that is what they were looking for, three things: 23% increase in capacity, firing rate, and charge pump limitations. So they gave us the base case and the design case, and the main thing was the pressure drop, the firing rate, and the extra duty. So they were looking at different options. And one of the options, the EPC involved in the project said it is not possible to improve the capacity of the existing heater. Foundations could be limiting, site works could be excessive. So they said, hey, let's just go for new heater. I mean, if you see the existing heater at 62 psi, they wanted to go with a less than 25 psi. And one of the things I want to share with you is everybody, including me, likes new heaters. So everybody, I mean, I don't want to say, but everybody likes new heaters. That's what they wanted. So they designed a new heater. They looked at a new clean radiant section, conventional radiant section, 40-foot long tubes on both the sides, 347, 8-inch tubes, 8 burners. So everything looking great. They put a convection section in the process service, 3 bare rows, 3 fin rows, and then they put a waste heat recovery coil, reduce the flue gas temperature to 500 degrees. So stack was 60 foot tall. That's what they designed. This is how the new heater would have looked like. Everything looking good over here. And they were able to meet all the three things. They were able to meet the process duty. They were able to meet the pressure drop. They went down to 15 psi. And they were able to meet the firing rate limitation. In fact, they were at only 49 million BTU. So basically, and the heater efficiency was 87%. So whenever we are talking of new heater, you're not only talking of just the heater supply, actually. You're talking of it requires new foundations, it requires new ladders, platform, all structural. It requires new inlet piping, outlet piping. It requires all electrical instrumentation work. And the time required is typically 12 to 14 months. That's what the typical required. And most of the time, the industry thumb rule is the cost of the heat, the total installed cost of the heater is typically 3 to 5 times the supply cost of the heater. So design engineering supply, if it's 1 million, the total installed cost is 2 million or 2 to 4 million, sorry, 3 to 5 million. So that's typically how so the client, the EPC and the client, they worked out the cost. The approximate cost was about 1.9 million. Installation was 1.5 million. And then if you look at the foundation, structure, piping, electrical instrumentation cost is 2.6 million, total installation cost of 6 million. So the total installed cost was 7 million. And they would have installed this heater. I mean, at the working level, everybody was going with this new heater. And when the investment thing went to the company board, one of the members asked, have you looked at revamping of the existing fired heaters? And the client's engineer said the EPC looked at it and they said it is not possible. So they said, okay, why don't you call furnace improvements and ask them to look at one more time and see whether any options are available for revamping the heater. So they came to us and said, hey, we have got only 2 weeks. Within 2 weeks, you give us the revamping options if it is possible to revamp the heater. And they were thinking that the most probably the answer is going to be no, so that they can go ahead with the new project. So we looked at their data sheet, operating data, this thing, and we came up with 3 revamp options. We told them we can replace the existing coil with 8-inch tubes and give you a new convection section. Keep it a 2-pass design. We can also give you a 5-inch coils in 4 passes and a new convection section. And the third is we can only replace the convection section using our patented split flow technology. So we made these 3 present options to them. In the first case, we basically were retubing the radiant section with 8-inch tubes at 16-inch pitch and putting a new convection section. And by doing this, we were able to cool the flue gases all the way to 562 degrees F. This is how the thing looked like. The proposed heater option, revamp option looked like. The second option was using 4-inch, four pass 5-inch coils at 10-inch and giving them a new convection section at the top. And this was also working out good. The flue gas temperature was 592, and we were able to meet all the 3 parameters. And this is a sketch of the revamp option 2. And you can see over here, these are the 2 options we are telling you. In the first option, the pressure drop was reduced to 15 pounds. The second option, the pressure drop was reduced to 21 pounds. And they were both meeting the client's requirements. So those were the 2. This is basically giving you a comparison of detailed comparison of the operating data. You can see the pressure drop went down to 14 and 21. We were able to reduce the firing rate to almost like 27. So that was very good actually, good efficiencies. We were still able to generate some steam, firebox temperature and bridge wall temperature and fluxes, everything was in control. So what we told the client that there are a few issues with revamp options 1 and 2. One is the radiant coil is heavier than original because it is larger diameter. It weighs 5 to 8,000 pounds more than the original. We will need new radiant tube supports. Arch will have to be modified. The new convection section will be heavier by 27 to 31,000 pounds. So furnace steel reinforcement modifications are needed to withstand extra weight, and it will have a longer turnaround time and site work. So we gave them these options and we told them these are the limitations of option 1 and 2. And then we gave them the third option. We said, okay, you can revamp your heater just by replacing the convection section. Use our split flow technology. We will divide the feed into 3 parts. 30% will go into the convection section and 70% will continue to flow in the radiant section. And then we will combine them at the radiant outlet. And we were able to reduce the flue gas temperature to almost like 530, so lowest temperature. And this is how the flow control scheme looks like. If you see, all we have is a third pass where we are putting 30% flow. The 2 passes are being 35% flow. And there is a TIC which is controlling the flow to that convection pass. So, and then the master TIC is controlling the fuel gas flow rate. So very, very simple scheme we propose them. And if you look at it, we are only changing the small convection section what they had and the 4 arch tubes. This heater had also a steam drum. We are not touching the steam piping or steam drum. We are still saving that. So very, very minimal modification. You can see that's what we ended up doing actually. So this was the heater before revamp. And then we replaced the convection section, and we were able to get what they were looking for. We did replace 4 radiant tubes in the top at the arch and made it a part of the third pass because we wanted to balance the heat and the pressure drop. So we did do that. But basically, just by doing this small modification, we were able to give them all the 3 parameters. So if you look at it, we were able to get process duty up to 37. We were able to optimize the pressure drop all the way to 20 psi. Allowable was 25. You see the mass fluid velocities are pretty good. We were able to keep the firing rate down to 49. Actually 55 was the limit, and we were still able to get them the waste heat recovery, and the overall efficiency was 85%. So in our mind, basically it was the best option to go for. And you can see these are the 3 radiant section modifications. In the first 2 modifications, we are changing the tubes. And in the last modification, we are not touching the radiant section except the top 4 tubes. So a lot of modification was needed with option 1 and 2. And these are the cost estimates of option 1 and option 2. And you can see both the options 1 and 2 were costing about $2.3 million. The option 3 was $1 million. Now you will also see we would have made more money if you would have sold them option 1 and 2, And in option 3, we only made half the money. Our fee was almost half of what we would have charged them for option 1 and 2. But we did the job for less than $1 million. And the client gave us, and we executed it. So lower cost, that was the advantage. You can see the convection section in this picture. Lower shutdown time, no structural modifications required, no civil works foundation required, and better performance. So this is a picture of split flow convection section for that project when it was being fabricated. As you can see, it looks like a very small convection section. That is with the end tube sheets. This is with tubes which have been put in there. So our cost was less than half of the conventional revamp cost. So we try to provide you with unique solutions as part of your team and give you the best available for your heater. Here are the revamp jobs, which are split flow references we have done. The first one which I showed you was for Citgo Corpus Christi number 4 platformer heater. We saved our client 50%. The second was for Valero in Texas City, where we put this platformer split flow in not only platformer, but in naphtha hydrotreater units. Then we did this reactor charge heater of the case study, which we told you. And the client liked our split flow so much that we ended up putting in 3 more heaters, 1 in the hydrogen heater and 2 in the reboiler heaters. Similarly, Valero gave us another project in Wilmington to put this split flow project. Phillips 66, we did a job for Wood River Refinery where we installed the split flow. And in HPCL Mumbai, we installed it in 6 heaters, extract and raffinate heaters. And it's been working very, very nicely from there. So in summary, what I would say is we are giving you capacity improvement and optimizing the pressure drop. An additional pass in convection section can increase the capacity by 20 to 25%. No need to modify the radiant section. It is low cost revamp as compared to the conventional revamp. It can save you $1 million. It has been proven, and working well for so many clients. Let us know if we can install it in your fired heater. Contact us at info@heatflux.com. and we will try to give you the best possible technology. So thank you very much, and I look forward to answering your questions now. Please give me a minute to see the questions panel over here. Hey, Ambreen, can you help me here? How do I see the questions now? Hmm? Yeah, that's okay. Yeah. Yeah. So I want to see how can I. So the first question I got is, I don't know how to. I'm still at new webinar, so give me a minute to fix it. Okay, so with the reduced flue gas temperature, is it recommended to combine this technology to a furnace with an existing pH? I don't see any problem. This is irrespective whether you have an air preheater or you don't have an air preheater. It will be, it can be installed actually. I don't see any issue. Any other questions which we have? If anybody has any other questions, please let me know and I will try to answer them. We still have a few minutes left, 5 minutes available. So the next question we have is, wouldn't the additional tubes in the convection section affect the draft of the furnace? Is the furnace stack damper enough to maintain the draft with this technology? Absolutely. So we do a complete re-rating of the furnace and we want to make sure that any additional surface we add, you still maintain the draft, enough draft in your heater. So the heater is completely re-rated. It's not just the convection section. We re-rate and make sure the stack, the burners, everything is working. So good question, because convection section, we can always increase the width, you know. Okay, I got it now. what kind of revamp we have to do if you want to use furnace with design duty of 11 megawatt at a reduced the duty to reduce with 30%. Uh, I think you have to re-rate the heater at a lower duty and make sure that the burners can be correctly sized. Also, the stack and the minimum tube metal temperature so that there is no dew point corrosion in the heater. So, what is the revamp duration downtime of the unit? Uh, Typically, since we limit our modifications to the convection section, and convection sections can be fully shop fabricated, so the time for most of these projects has been like 2 to 3 weeks, depending on what other modifications which we are doing. What are the methods to control tube skin temperatures? Only by adjusting the firing in the burner or any other method uh, when the burners have adequate capacity. So this webinar which we are doing today is mostly for uh, split flow capacity today, but we will definitely have another webinar where we will discuss the burners. The main thing is you have to make sure you don't get any flame impingement. And that's what we will focus on our next webinar, how to make sure you don't have any flame impingement and you can lower your tube metal temperatures. The split flow technology appears to be very simple. Why wasn't it considered in the past? Is the control of the split flow critical? What about the draft limitation? So good question, Craig. I think there are so many things we don't know why it was not considered. I think maybe historically it was not needed actually. And the split control of the split flow is not critical. We did our first project by just using orifice plates. It is not something which we have to do it, but there are some clients uh, uh, who want to have the exact temperature. But if you're not worried about exact temperature, we could just put simple orifice plates and divide the flow actually 30 and 70, so that it can be done that way. The new heater had platforms on the stack. Was that for SAM's? Nice. Yes. SG stands for steam generation. So how does the split flow technology affect the draft? No, it does not affect the heater draft. I think we make sure that your heater has sufficient draft even as before. So your firing rate, you are not draft limited after split flow, and you have plenty of air and plenty of uh, fuel you can fire still. Have you done split flow with vertical can heaters? Yes, we have done split flow with vertical can heaters. We did uh, two projects, the two heater for Philips 66 reformers were vertical can heaters. The two heaters in fact, three heaters for Delec were vertical can heaters. Yeah, it can be done. Has this been evaluated on delayed cooker heaters? If so, how do you handle the skin temperature on the turn down? So we have not looked at delayed cookers. Delayed cookers, as you know, are the critical heaters, and it can be done, but we have not looked at it. I think there are other ways. Do you have a reference in Europe? No, our references are mostly in US. Can you apply this technology to crude atmospheric furnaces? Yes, we are working with two of our clients uh, on applying this technology to crude heaters. We have done the engineering study. We have also done the PDB study. So we are just waiting for the execution. And there what we are trying to do is to reduce the pressure drop. And the split flow basically offers us a way to shift heat from the radiant to the convection. So the one of the things we are doing there is trying to lower the heat flux. Can CO emissions occur if the radiant section is too large? Normally CO emissions do not occur if the radiant section is too large. CO emissions occur if you go down, if you have bad combustion, or if your flame temperature or firebox temperature goes down very, very low. Thank you all. We will try to send you the answers. I think so. There was your examples are for retrofits. Would split flow technology be advantageous for new fabrications? Why not? I think it can be done even for new heaters. I would say for platformer heaters, you can always go and reduce the size of the platformer. You can reduce the size of your you can reduce the firing rates. And if you don't need steam, you can have a value heating actually. You had platforms on all three stacks, yes. No, so the draft, I mean, we just want to let you know that we make sure that the complete heater is rated and the draft is never an issue actually. So well, thank you all. I have tried to answer all the questions. I do apologize, I'm still new. And we will try to answer these questions and post it in our webcast. Thank you all. Have a nice day.